Hello and welcome to the Oxidation and Reduction in Electrochemical Cells read-along for Chapter 4 of the General Chemistry book for Berkeley Review. This is part 4, the final of 4 parts. My name is Todd Bennett. If you listen to the first 3, you probably know this. I'm the General Chemistry teacher and Physics teacher for Berkeley Review in Southern California, the Irvine and Westwood Centers. From teaching classes, this has certainly helped me to write the book, and so I'm also the author of this book. And I want to just give you a little insight before we start into this section. This is the tail end of the chapter, so from page 164 through the end. And the way I've designed my books, and you probably have noticed this as you've gone through the various chapters, is that the first portion is usually more of the foundation, the fundamental information. And certainly what we've done to this point, we've balanced redox equations, we've studied EMF and how to calculate voltages. We've applied it in electrochemical cells. We've done the informational basis. What this section does is this puts it all together into more MCAT realistic topics. So a lot of these are machinery, devices, applications, systems that apply the terminology, the technology. So we're going to look at the Nernst equation and how concentration has an effect. Going to look at an electrolysis, galvanizing, some of the processes that we apply and take advantage of through this section. So as mentioned, it's the tail end of the chapter. We're going to cover figures 4.9, 4.10. We're going to do a lot of examples. This is mostly questions, so examples 4.10 through 4.16. And my goal is that this is a section that you can really look at things and make quick decisions. You have to be able to answer questions on average in a minute. Our goal is to build you to a point you can average maybe around 30 to 40 seconds, which gives you a big bundle of excess time at the end of your exam to go back and review what you need to, catch your careless mistakes, and ultimately raise your score. So speed matters. This is the section. We'll get into that. If you read through what the homework goals are, phase 1 is one where you just reaffirm with the information. Phase 2 is where you worry about timing and applying it. And then phase 3 is where you get the most MCAT realistic scenario. The chapters kind of set up that way. So this is kind of, if you will, the phase 2 and phase 3 for the review portion. So I want to start with the concept of what happens to any electronic device that runs on an electrochemical cell over time. If you, ever notice with your cell phone, your computer, the voltage stays relatively constant until you get that warning light saying you better plug in or it's going to crash on you. And so the above graph pretty much dictates or explains what we see. Battery stays constant until it dies at the end. So if you notice the similarity of this curve to the titration curve region, the buffer region of titration curve, you should notice that just like that one, over time in titration, as you consistently add in some titrant, the pH stays relatively constant and then suddenly changes. This is where the cell voltage stays relatively constant and then suddenly changes, which means we're dealing with a log scale. And so here's the picture I want to throw. I want to shrink it down to a different size from what's in the book and analyze it. So again, it's going to stay relatively constant and then suddenly drop. Well, the equation that explains this is the Nernst equation. The derivation of it is not as important as the application. And I think that's true of every equation. I've said this a few times, and hopefully you buy into this. But notice a similarity when we have pH equals pK plus log of base over acid. This is E cell equals E naught, a standard value like a pKa, equals log or minus log of products over reactants like base over acid. The only thing it's multiplied by a constant, a conversion term, but it's very similar. And that's why the graph has the shape it does. So a few things you should note is over time, Q is going to change. So as reactants go down and products go up, products over reactants becomes a bigger number. Log of Q, as Q gets larger, log of Q will get larger, but it isn't until it gets extremely large that number value is going to be high enough to cancel out the E naught. When that finally happens, once it reaches whatever the equilibrium is, when the Q has reached the equilibrium state, voltage is going to drop to 0. So it's a rapid change because fractions change drastically when the denominator is approaching 0. So let's consider an application of this Nernst equation. So we want to consider a nickel palladium cell. So if you look back at the table, you'll be able to add the 0.99, the 0.23, and you'll get a standard cell voltage of 1.22. Plugging into the rest of it, where do the numbers come from? So 0.059 over N, palladium's 2 plus, nickel's 2 plus. So in the balanced reaction, you're transferring 2 electrons. So the 0.059 gets divided by 2, leaving you with a 0.003. And then it's products over reactants. The cathode is palladium getting reduced, so palladium 2 plus is a reactant going to palladium metal, hence it's in the denominator of the cube. Nickel metal is being converted to nickel 2 plus in that oxidation reaction, that's why it's in the numerator. So it's products over reactants. I'm not as concerned with how it's set up in this case, I'm concerned with how the ratios are going to affect it. So if we consider a scenario where the reactant is in 10 times the concentration of product. So if you think about it, it's when your battery is maybe 90% charged, 95% charged, what voltage will we get? It's mostly reactants at that state. So it's going to be 0.122, the cell voltage, minus 0.03 times log of 1 over 10, products over reactants. Log of 1 over 10 is negative 1, negative of negative is positive, so it's 1.22 plus 0.03, grand total of 1.25, which is basically the original cell voltage, the standard cell voltage, 1.22, plus a little bit. That 0.03 is kind of trivial. So from a GChem perspective, the impact of concentration is not that significant. Hence, that's why from 90% to maybe 50%, the voltage is only going to change from 1.25 to 1.22. Now let's consider the inverse of that, the scenario where you have mostly products and very few reactants. So maybe when you have like 10% life left, in that case, the cell voltage, again, 1.22 minus 0.03, but now times log of 10 over 1, because it's more products and reactants. Log of 10 over 1 is 1, so it means minus 0.03 for a 1.99 volts. So from about 90% full to about 10% full, you're going from 1.25 volts to 1.19 volts, which is why if you look at that line, it descends slightly in, I'm going to refer to it as a buffer region, but probably should refer to it as the constant voltage region. Doesn't change much. Your battery really ends up doing the same thing the entire time. But when you get, again, to a point where the denominator is getting really small, then the value of that fraction is going to start changing drastically as the denominator continues to go down. I'm going to subtract more and more and more. But for the most part, this tells us that our voltage is relatively constant. Keep in mind the Nernst equation is also used in physiology. So you've done this in terms of action potentials. So consider ions inside and outside a cell that are not undergoing an electrochemical change. Typically sodium and potassium are the ones we're thinking about. There's no E naught because there's no reaction. So it's strictly the 0.059 over N, charge is plus 1, so they usually drop it out, times log of out over in. Just note that that's a millivolt scale and not a volt scale. So this is volts, which is why it's 0.059. In the Nernst equation for physiology, it should be 59, and actually because the temperature is higher, we usually plug in 60. But it's the same equation without the E naught. So you're using the same thing, that one you're just looking at relative concentrations. So it's a useful equation. You're going to run into it in homework in both the GChem and the physiology. Be able to apply it in both. So here's a unique way of doing cell voltage. This was drawn as figure 4-5 earlier, if you have questions on how it's set up. But reading left to right, when they do it this way, it's the anode separated from the cathode, and it's reactant before product. So for instance, choice A says that in the anode, zinc metal is being converted into zinc 2 plus, and at this point in time, the molarity of zinc is 0.1 molar. And then on the opposite side, the cathode side, you have copper 2 plus being reduced into copper solid, and the copper concentration, copper 2 plus concentration, starts at 1 molar. So the greatest cell voltage, if we think about the Nernst equation, is a combination of E naught and the relative values of product over reactant. So I want to keep this as simple as possible. So we'll start by looking at the cell voltages for the half reactions. Using table in the book, you'll note that zinc reduction is positive 0.76, the inverse of what's shown in the table, and copper is positive 0.34 for an overall voltage of 1.10 volts. Nickel, 0.23 for the oxidation, the opposite of what's in the table, and then silver is a positive 0.8 for reduction. So the greatest voltage is going to be associated with the solution that has the highest E naught, which in this case is copper zinc, and the one that is richest in reactant. As we saw before, when you have more reactant in product, it's going to be E plus a little bit. So there's our equation. So 1.10 is higher than 1.03, just as I'd walked through. I'm hopeful that if you weren't following, you stop the video, look back at that table, read the numbers, write it down on a piece of paper, and then come up with a 1.1 being greater than 1.03. So we've eliminated the copper zinc. Now it must consider which is the more reactant, which is the more product. So in choice A, you have 1 molar reactant and you have 0.1 molar product. In choice B, you have 1 molar product and 0.1 molar reactant. So zinc 2 plus is a product cation at the anode, copper 2 plus is the reactant cation at the cathode. So again, choice A, you have 0.1 product over 1 molar reactant. In choice B, you have 1 molar product over 0.1 molar reactant. You want the one richer in reactant. You want choice A. So more reactant product means it's going to be slightly higher than 1.10. Choice B is going to be slightly lower than 1.10. You do not need to calculate this fully. And that's a problem I think most of us have, is we're trained to always show all our work, box our answer, get an exact result. Because it's multiple choice, you really need to focus on doing things conceptually. So we're looking for the greatest E naught, the greatest standard voltage, and the most reactant. And in this case, choice A had the greatest reactant for the reaction that had the greatest voltage. 4.11. What is the voltage of an electrochemical cell with an anode of zinc metal and 0.1 molar zinc nitrate? So the other end, you have 1 molar silver nitrate. So this is plugging in. It's a calculation. So the standard voltage for silver, 0.8. The reduction of silver is, and then 0.76 for the zinc oxidation. So overall, we have 0.8 for one half reaction. We have 0.76 for the other half reaction. So we start out with a 1.56 voltage for the E naught of the reaction. Now it's a matter of plugging in the Nernst equation, which we do by deciding which one's a reactant, which one's a product. Zinc is getting oxidized, so zinc 2 plus is a product. Silver is getting reduced, so silver metal is, silver cation is the reactant, silver metal is the product. So zinc 2 plus is over silver plus. Zinc 2 plus, again, it's a product. Silver plus is a reactant. And in this case, then we have to decide what our N is. And this gets a little bit tricky. Because you need 2 electrons for the zinc half reaction, you need to do 2 of the silver reactions to get those 2 electrons. In the balance equation, you would end up with 2 electrons, so I'm going to divide by 2. So in this case, you have 1.56, the E naught, minus 0.059 divided by 2 electrons per balance reaction, log of products over reactants, 0.01 zinc 2 plus over 1 molar Ag plus. So it becomes 0.03 times log of 0.001, which is log of 1 over 100, which is minus 2. So 0.03 times a minus 2 is going to be 0.06. The minus going to cancel out and become plus. So you end up with 1.56 plus 0.06 for a final voltage of 1.62 volts. Okay, a lot of math, and I'm plugging numbers in. And again, you might have had to stop the video to try to decide where everything is. Definitely worth your time to write the balanced equation for this if you needed to. But I don't need to do all that. What I should do is look at the answer choices and realize the E naught was the most important number you'll cover. We're doing GChem, and in GChem, the cell voltage is E naught plus or minus a little bit, depending whether it's rich in reactants or rich in products. So ignoring the math completely later on, just looking strictly at the E naught for the overall reaction of 1.56, I know that the best answer is going to be around 1.56. So I should have gotten rid of A and B right away, knowing that concentration is a trivial factor, a millivolt factor, and E naught is a volt factor. Then I need to consider what the reactant products are. So it said anode of zinc metal, and in the anode you get oxidation, so the zinc cation is a product, so I know that it's 0.01 product. It said a cathode of silver metal. Well, cathodes are where cations get reduced, so 1 molar silver plus is the reactant. So I have 1 molar reactant, 0.01 molar product. It's richer in reactant than product. So the final voltage, the overall voltage should be this E naught, 1.56, plus a little bit. So you're looking for a number just barely greater than 1.56. Far easier to do it conceptually than it is to do the detailed math. Math is where you run into errors, especially if you didn't realize the 2 and you plugged in a 1 and the number you want isn't there. You're going to be going for the closest number anyway. So do things conceptually, even if they look like a math question. Example 4.12. What is the cell potential for the following reaction used in a typical car battery? So you have lead reacting with lead oxide. So lead in a 0 oxidation state reacting with lead in a +4 oxidation state, both ultimately ending up in lead sulfate where it has a +2 oxidation state. They give you the respective half reactions, and the important thing is for you to realize that you do not need to multiply for the balanced reaction. You just have to simply put the two reactions together. The problem as it is the upper reaction for PbO2 is written correctly, but the lower reaction for Pb is backwards. So I need to flip that reaction around. So 1.69 stays as it is, but the second one has to be reversed to make it, instead of negative 0.35, positive 0.35. The sum is 2.04. So it ends up, this has absolutely nothing to do with the Nernst equation. This is one of those review questions from earlier in the chapter that I threw towards the end, just to make sure you're still moving along. If you're tunnel vision on Nernst equation, doing a question that suddenly has nothing to do with it makes you go back to that neutral setting, that how do we look at a general question. So the big things on this one are to try to figure out where the wrong answers came from and why people would have come up with this. So choice D, if you would have multiplied everything by 2, you would have gotten that number. So somebody might have looked at 2 PbSO4s and made some decision. You either multiply by 2 or divide by 2. Those wrong answers are there, tempting wrong answers. And if you would have forgotten to reverse the negative 0.35, you would have got choice B. So there are tempting wrong answers. It's one thing to try to do, because that's definitely something the MCAT test writers do. Your job, stay focused on what the right answer is. Fairly straightforward question if you just systematically go through it. Okay, so 2.04, perfect answer. 4.13, why would it be dangerous to use fluorescent lighting in sawmills? What the heck does this have to do with anything? So again, trying to throw things that are vaguely related. So here's my reasoning. Electrochemical cells generate electric flow. Electric flow is current. Current be used to power devices. This is a device. It's a loose connection, but here's a physics question that has absolutely nothing to do with anything in this chapter, buried in the middle of your GChem. Again, kind of preventing tunnel vision and making you think beyond just the scope of what the chapter is on. So I want to start with the notion that lighting runs on AC current, whereas the batteries we're making, you have a distinct cathode and distinct anode in electrochemical cells we were discussing. So everything that I've done in electrochemistry so far has been DC, direct current from the cathode to the anode, keeping in mind currents in the opposite direction of electron flow. So if I want to say direct electron flow from the anode to cathode, it doesn't go one direction and change. It just goes in the one direction. So for fluorescent lights, they run on AC current, which means technically they are a strobe light. They're on, they're off, they're on, they're off, and they have a certain frequency. So this is just pointing out that current is AC that we use for our household appliances. It is going to flash at a certain frequency. So that frequency is going to have some impact on any other device that's periodic, i.e. a spinning blade. So if a sawmill is a spinning blade that, let's say, is going at, let's say, 600 revolutions per minute, if the fluorescent light were also fluorescing and flickering at 600 flashes per minute, then they have the exact same frequency. They are so-called in phase. So every time the light would flash, the saw blade would look like it's in the exact same position. This can also happen with harmonics. And so harmonics is going to be a chapter to itself in physics, or a section to itself. But for harmonics, we are dealing with similar thing to being in phase, but maybe in phase with every second flash. So for instance, if the strobe light was twice as fast, twice as frequent as the spinning blade, then the blade might spin twice and it flashes, and you still get the optical illusion of being in the same spot. So independent of what harmonics and phasing is, still want to just look at this question on the whole. So the tubes are emitting light at a certain frequency that could deteriorate lubricants. That's just not, that's just a throwaway answer. Just definitely not what we're dealing with here. The tubes could emit light that decompose wood. Well, if that were true, sunlight would have destroyed it long before the wood ever got into the sawmill. So those are throwaway questions that are tempting because they're talking about, I guess, a chemical process or an organic chemistry material, but just not applicable. The tubes could emit light in phase with the saw blade. That's our concern, in phase or in harmony. And then the tubes could initiate combustion. Well, whether the saw blade was there or not, you could wood would catch on fire. That's just our throwaway answer. Light would set all wood on fire. Force would never exist. So best answer here, the frequency of the saw blade could be in phase or in harmony with the frequency of the lights. Again, nothing to do with GChem, just one of those things that throw you off the scent a little bit. 4.14, why is a filament thin, or why is the thin filament made of tungsten? Again, random question. This one is a little bit of both, because actually we have to consider both the fact that a circuit is occurring, that's physics, but then the material we're choosing is a chemistry question. So we want to determine whether a thin or thick filament offers more resistance and what we actually need. So we're trying to generate a lot of heat drain. Power drain in physics is I times V, current times voltage, but it can also be rewritten as I squared R. So to maximize the amount of energy coming out of a filament where you want the greatest drain, you want high current and you also want high resistance. So it's kind of a double-edged sword here. So because you want to heat up, it gives off light. So again, we want to have maximum resistance. So I'm going to eliminate the minimum resistance, and the thin part is in all the answer choices, so I got a break on that. I didn't have to worry about it. But the maximum resistance, because I squared R, I want maximum R. Okay, so now for what I want from the tungsten filament. If the tungsten filament had a very low thermal coefficient of expansion, then it won't expand, and that sounds like it's kind of useful. I mean, that could be definitely beneficial because you want it to stay the same size, because changing size could change resistance. So A is a tempting answer. The tungsten is used because of its high heat of fusion. Well, heat of fusion is the melting point, essentially. And so if you have a high heat of fusion, it takes a lot of energy to melt it, you have a high melting point. Very useful in this situation because if the tungsten filament melts, it's no longer a filament. It's no longer a solid, current doesn't go through it. So that's definitely essential. And then you want tungsten because of its low ionization energy. That's definitely not a right answer. You do not want it to ionize and turn into tungsten cations, because then you'll lose them. They won't conduct material anymore. So I can at least get rid of choice C. So ionization, that's gone. It's a decision between, do we worry about if it expands or melts? The bigger concern is that melting would break the circuit, expanding would weaken the circuit, but it would still work. So the best answer is because of the high heat of fusion, the high melting point. So the best answer, choice B. Electrolysis. We're on to a few applications. So electrolysis using electric current to break something. The typical textbook example, and the one that I follow as well, is the breaking of water. So if you put current into water, you're going to convert the H's and O's in water into their elemental state. So H has an oxidation state of +1 when it starts and finishes as H2 with 0. O has an oxidation state of -2 and it finishes with 0 in an oxygen molecule. So H is getting reduced, so it should be the cathode reaction, and O is getting oxidized, so it should be the anode reaction. Again, the battery dictates everything. Little orphan Annie, little anode, fat cathode. So on the battery at the top, the little anode is pushing current, pushing electrons, if you will, to the cathode. So the cathode is on the left, and then the large electrode, the cathode of the battery, is pushing current or electron flow to the anode. So that's my picture there. Again, I want to look at an updated picture so I can draw on it. So again, here are my issues. There's my overall reaction, so I got to put voltage in, I got to put current in to make this happen. That's why the battery's there. The applied voltage, as long as it's greater than 1.86, then that anode can push charge across and make the reaction occur. So we have the anode of the battery on the left making the cathode of the solution on the left. The cathode on the, or the electrode on the right of the battery is the cathode, making the anode, the one on the right, in solution. So anode's always connected to cathode. Electrons flow from anode to cathode, red cat. So the reduction is going to occur at the cathode. The reduction reaction was H plus gaining 2 electrons. Oxidation of the oxygen, O2 minus is going to O0, so it's losing 2 electrons. That's the oxidation reaction. That'll be the anode. This is why H2 bubbles form at the cathode, O2 gas, O2 bubbles form at the anode. What we have done is we've carried out a reaction that made pure H2 on one side and pure O2 on the other. Completely up to the scientists what they do with this, but if you collect the two separately, You can use it for purifying gases. That's one of the techniques for purifying gas. A very common one is use electrolysis. You can also use these same two gases, funnel them into a combustion engine, and have an engine that runs on hydrogen. So the hydrogen fuel cell is based on this concept where you generate hydrogen and then use that as a material for fuel later. So a question, when a voltage is applied to a following reaction, the electrochemical cell below, what is true? The gas is formed at each of the electrodes in solution. So I once again have to look at what's happened here. In this case, we have H in water starting out as +1. We have it finishing in H2 gas as 0. So that's reduction of H just like we saw before. So H plus is being reduced into H2 gas. The interesting new reaction in this case isn't the same one we just saw in the example before, in the figure before, but it's chloride going from Cl- to Cl2 gas. So that's actually the oxidation now, from Cl- 1 to Cl0. So the same setup as before. The battery is the anode on the left, cathode on the right. That means that the cathode in the solution is the one on the left because it's connected to the anode. Likewise, the cathode is the right side of the battery, so it's going to connect to an electrode in the solution on the right being the anode. H is getting reduced, so H is going to form at the cathode. Chloride is getting oxidized, so it's going to form at the anode. So we can right away get rid of the incorrect choices. So H2 bubbles on the left, not the right. We're set on that. And then Cl bubbles on the right, not on the left. The second part of the question is the pH. It has nothing to do with electrochemistry chapter, but certainly fair game for what they want. This one is hopefully straightforward in that the product you're generating is OH-, a basic compound. Add base into solution, pH is going to gradually drift up, meaning over time, you're going to have an increase in pH. The best answer, A is in awesome. Last applied subject here is the concept of galvanizing. Because we live in an oxygen-rich environment, materials oxidize. It's just what they do. So we have a couple choices. We can try to coat them and prevent them from coming in contact with oxygen. That works to a certain point, but eventually coatings deteriorate and things are going to rust away anyway. Or we accept that it's what it is, and we put a sacrificial material. So iron is the material we usually are worried about and what we build from. So let's say you make iron pylons for some building or some parking structure. Over time, they're going to oxidize away in the air, and it's going to compromise the integrity of that structure. So to prevent this from happening, especially in an area where you're rich in salt water or any sort of abusive weather, you want to put a metal that's going to preferentially react. So I propose let's put nickel there, and I want you to tell me or say to yourself whether this is a good plan. So I'm looking for something that's more reactive than iron, that's going to be oxidized in lieu of iron. And if I were to use nickel, well, that's only 0.23. The oxidation of iron is 0.44, so putting nickel on there wouldn't help. Iron would get oxidized anyway because nickel is not reactive enough. So let's go in the other extreme. I propose let's try sodium. Sodium at 2.71 is definitely more reactive than iron. It's by all means going to react instead of iron, but I've overdone it. This one is too reactive. If you put sodium onto any structure, first time any water is exposed to it, any rain, any moisture of any type, it's going to react violently, and you'll have far bigger problems than oxidation of iron. You'll have a problem of your structure just blew up. So we want something more reactive than iron, but barely more reactive. So the actual metal they use is zinc, zinc 2+. That's why it's presented in the question, but you want something a little more reactive. And by putting zinc on there, zinc will slowly erode instead of iron. Eventually you're going to run out of zinc, in which case you just add more zinc. So galvanizing is continually adding a more reactive species, in this case zinc, to protect the species you want to preserve, iron. So last question in the chapter. Which of the following metals can be used to galvanize steel? So we just went through it, and part of the reason I wanted to present those other examples is so this question will go a little bit easier. So we want to galvanize steel. Well, iron's a major component, so you don't really add your own material to it to preserve it, so that's out. Nickel, we learned at 0.23 was not reactive enough, so that one won't work. Potassium, just like sodium in the previous example, was too reactive, explosive. Zinc is the metal we choose to make this work out. So again, not reactive enough for nickel, too reactive for potassium. Perfect example. The one that's just barely more reactive than iron is zinc. We galvanize with zinc. So this last section, the one I just went over, Lots of the things in there make up your questions and your interesting passages on the MCAT. Make sure that these are honed in and pick them up through the phases. So this is the end of this 4-part series. Again, I want to thank you so much for using our books. It really means a lot. It means a lot to me. I mean, it's a work of love. Creating these books has been an ongoing passion for some time. And when you do well, a piece of me does really well. So thank you for being a part of it. And best of luck on the MCAT.